Welcome to 3-4 day 2. We're still, solving exponential and log equations. And here in example 5, we're going to solve an exponential equation of the quadratic type. Now these, the first time you see it, it might be kind of weird, but after that, hopefully you'll recognize them. We want to factor e to the 2x minus 3e to the x plus 2. And what usually throws some people for a loop is that first term. You know, if that was an x squared, we would start off by putting an x here and here, because x times x is x squared, because when we multiply the same bases, we add the exponents. Now here it's e to the 2x, so we should have a base e and a base e, and when we add the exponents, they should add up to 2x. What adds up to 2x? X times x. And now the rest of it's like factoring a regular old quadratic. We need two numbers that multiply to positive 2, add up to negative 3. So that would be a minus 2 and a minus 1. They add up to the negative 3. They multiply to the positive 2. Now it's still equal to 0. And after we've factored, it does say solve. So we can set this first factor, e to the x minus 2 equal to 0. We can add 2 to each side. E to the x is equal to 2. And now natural log. We would natural log the e to the x, so that would just become an x. X equals the natural log of 2. If they're asking for a decimal, that's approximately 0.693. The other factor, e to the x minus 1 equal to 0, we would add 1. E to the x equals positive 1. And then we take the natural log. The natural log of this would just be an x equals, and then the natural log of 1. If you type that in your calculator, out pops a 0. If you think back to when we graphed the natural log function, it looked a little something like this. Here's the xy axis and the origin. All log functions go through this point, 0 or 1 comma 0, unless they've been shifted. When the input is 1, the output is 0. That's a good one to memorize. It does pop up pretty frequently. You'll hear it a few times in calculus. The log of 1 is 0. What's next? Oh, one for you to try. Okay, give it a shot. Again, it's going to be a lot like the last one. Don't let the e to the 2x power throw you. All right, so we'll have an e to the x times an e to the x. That gives us e to the 2x. Two numbers that multiply to 12, positive 12, that add up to negative 7. So we can tell right now these are both minuses, because they're going to add to a negative and multiply to a positive. And how do you multiply and get 12? 1 times 12, 2 times 6, 3 times 4. Oh, there it is. 3 times 4, they add up to 7. So we got a minus 3 and a minus 4. Okay, set each of these to 0. E to the x minus 3 is equal to 0. We can add 3 to each side. E to the x is positive 3. And then we're going to natural log each side. So now we get x equals the natural log of 3. And over on the other side, e to the x minus 4 is equal to 0. Add 4 to both sides. E to the x is 4. It's natural log time. So the ln and the e cancel. We have x equals the natural log of 4. If you like decimals, that nat log 3 is about 1.099. And the nat log of 4 is approximately 1.386. Okay, good stuff. Solving log equations. Make this a little bit bigger here. To solve a log equation, we can rewrite it in exponential form. So here we've got ln of x is equal to 3. It's in log form. X is stuck in that natural log, so we want to bust it out. What undoes natural logs? Bases. So we exponentiate each side, give each side a base e. X equals e to the 3rd power. Again, this procedure is called exponentiating each side of an equation. So let's take this for a test drive. Can I make this bigger? Yes. So x equals, the ln of x is 2. So we're going to base e and base e. So the e to the ln power cancels, and we've got x equals e squared. And the book, I believe, in the example just leaves it as that. We could punch it in the calculator and get a decimal, but I'm getting sick of decimals, so let's leave it as an exact answer. Okay, looking at this one. Log base 3 of this equals log base 3 of that. So this is a one-to-one property. We can set this equal to that. 5x minus 1 is equal to x plus 7. So let's see, I'm going to subtract x from each side. So now this 5x minus x is going to be a 4x. And then I'm going to get rid of this minus 1 by adding it to both sides. 7 plus 1 is 8. Ooh, this looks like it'll come out nice and clean. Let's divide by 4. X equals 2. It's always a good idea, too, to check your answers to make sure you don't have an extraneous answer. And it's real easy with logs. Remember, you can never log a negative. So let's plug this 2 into here. 2 times 5 is 10 minus 1. That's positive. Nothing to worry about. 2 goes into here. 2 plus 7 is 9. It's positive. Nothing to worry about. Part C. Okay. Now, before we can apply the one-to-one property, we need one log equal to another. There's our equals. On the left side, we've got a log minus a log. So before any one-to-one property can come into play, we're going to have to condense that left side. Log base 6 minus log base 6 will be a log base 6. And now it's going to be a fraction. The minus sign turns into a division bar, a fraction bar. Numerator was what was first, the 3x plus 14. The denominator comes after the minus, so that'll just be a 5. And that's equal to, whoa, there we go. That's equal to log base 6 of 2x. So we've got a log base 6 of this is equal to a log base 6 of that. We can just set them equal. 3x plus 14 over 5 is equal to 2x. And now we just got to solve for x. It's not so bad. I like to get rid of the fractions. Let's clear the fractions. If we multiply by both sides by 5, multiply by 5 over here, they're going to cancel. And we'll multiply the 5 by 2. That'll be a 10x equals 3x plus 14. Ooh, this one will come out nice and even also. Let's subtract 3x from each side. 10x minus 3x is 7x. That's equal to 14. And if we divide both sides by 7, we'll get x equals 2. Now, we shouldn't have to worry about an extraneous solution on this procedure, but just to get into that habit, let's do a quick check. Plug in a 2. 3 times 2 is 6, plus 14 is positive. 2 times this 2 is 4, that's positive, and here we have nothing to worry about. We're just logging a 5. So no extraneous answers, no bad things are going to happen there. Okay. Example 7 says solve this logarithmic equation, approximate to 3 decibels. Okay, let's see it. Locate our variable. Our variable is in this term. So let's get that term by itself first. We're going to subtract 5 from both sides. Subtract 5. 4 minus 5 is negative 1. Now we could move the 2 up and make it an exponent, but why deal with an x squared? Let's divide both sides by 2. The natural log of x is equal to negative a half. All right. Goal number 1, we've got our log isolated, in this case a natural log. How do we get rid of a natural log? We give it a base e. Base e. E to the natural log cancels, so we're left with x equals e to the negative a half power. And they did ask us in the directions to get this down to 3 decimals, so I would just go to the calculator. Negative 0.5, give it a base e. You should get approximately 0.607. Okay, I think next will be some practice problems for you, and there they are. Very similar to what we just did, so give those a try after you pause the video. No cheating, no peeking ahead. Okay, first one is all ready to go. ln of x is isolated, so we're going to give each side a base e. So now we've got x equals e to the 2/3 power. And let's just leave our answer like that. We could get a decimal, but they didn't say anything about rounding to 3 places, so we'll leave it as is. Next up, log base 2 of this is equal to log base 2 of that. So we can set them equal. We've got, oh, get back there. There we go. We've got 2x minus 3. We can set that equal to x plus 4. Subtract x, so now we're down to 1x is equal to, add 3 to both sides, x is 7. X is 7. And if we try 7 in each of our logs, we're left with positive numbers, so everything's good. Ooh, now we saw one like this in the example. On the left side, we're going to have to condense before we can apply a one-to-one property. So this will condense down to a single common log. The minus sign becomes our fraction. 4x is the numerator. Quantity 12 plus x is the denominator. And that's equal to the common log of 2. Okay, logs are the same. Log equal to log. We can set our fractions equal. So 4x over 12 plus x is equal to 2. Now to get rid of our denominator, we're going to multiply both sides by the denominator. If I multiply this side by a 12 plus x over 1, those are going to cancel, just leaving the 4x. And that's going to equal, I got to multiply this side by a 12 plus x to be fair. Distribute the 2, and that's equal to 24 plus 2x. Now to solve for x, let's subtract 2x from both sides. 2x equals 24. Divide by 2, and our final answer looks like x is 12. Nice. Was that the last one? Oh no. Oop, get out of there. I hid this one down here. I don't think we've solved this one yet. No, this is the one they want us to approximate to 3 decimal places. Let me get it here. And I like to identify my variable term. That's the only term that has an x in it. So first, let's get the underlined red term alone. 3 nat log x equals. We're going to subtract 7 from each side. 5 minus 7 is negative 2. To get the natural log of x alone, we're going to divide both sides by 3. So now it's negative 2/3. And since we got a natural log and x is stuck in here, we can break it out by giving it a base e. So now we've got x equals e to the negative 2/3. And I would be happy leaving it like that. But they did. The book does want us to approximate to 3 decimals. So on my calculator, negative 2 divided by 3 equals, give it a base e, 0.513 is our final decimal. Oh, and that's the end of the video. There'll be one more to wrap this up. I think we got a couple more examples to go, so I bet you're looking forward to that. You can play it right now.
Thank you.